A stack in C is simply a linear data structure that compiles with the LIFO principle, which is last in, first out, in which both insertion and removal occur from the same in, that is the top. A queue in C, unlike a stack, is simply a linear data structure that compiles with the FIFO rule, first in, first out, where insertion is performed from the back while deletion is performed from the front. By the end of this course, you are expected to have in-depth knowledge about stack and queue along with its implementation using C programming language. So stay right where you are and learn all that you can about stack and queues in C. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions and I will respond to your comments.
Now let's talk about stack. What is stack? Stack is a linear data structure. That means if the elements are stored in a stack, they will be stored in a linear fashion. Now it follows the principle of last in, first out, also known as LIFO. That means the element that entered at the end or in the last will be the first element that will be removed. As simple as that. Now you might be thinking, okay, it follows a principle of LIFO. Now does that mean its removal is restricted? Yes, it is. So you can only access the top of the element. That means this element is accessed. And how can you keep a pointer or keep a track of this top? With the help of this top index, this pointer or iterator that is kept for the tracking of the top of the element. So once you have entered this, the top will go up. Then you have entered this, the top will go up. That means you're incrementing top. And finally, the top is here when you enter this. Now, since you're removing this, that means only you have the access to the top of the element. You are removing this, then you will decrement your top. Okay, that's it. So with the help of this top iterator, you can keep the track of the last element, and you can also keep the track of the elements which entered in the stack. Insertion and deletion can take place only from the top, which is obvious, right? Let's suppose you're trying to insert the element. What you will do, you will increment your top and then insert your element. And if you want to remove it, you just decrement your top. That's it. So this is what you mean by pushing and popping, right? So the elements that you are inserting, that is nothing but your push operation, and you will increment your top. So elements you are removing is nothing but your pop operation. If you take an example of stack of plates, right, one after the other, the plates are stacked upon each other, right, one by one. So you can only access the top plate and you cannot access anything that is in between. So that is the restriction that is there. So in terms of stack, there are four major operations: push, pop, is empty, and peek. So push means nothing but to insert an element in the stack. So you're inserting. And now you might be thinking, okay, what is the time complexity of this push operation? Since we can keep a track of this, the top of the stack, right? With the help of this top, we can have a track of what are the elements that are on top, right? So only, let me just show you. Since the top is here, right? At this, now you want to push. So you just update your top, that's it, right? And you insert value. So this takes a constant amount of time. So inserting a value takes a constant amount of time. That is the big O notation, right? Big O of 1, that is constant amount of time. So similarly, we can remove the element and it can be done with the help of this pop operation. That means we can remove this top of the element just by decrementing our top. Once we decrement our top, this top of the stack element is removed. So now again, we are just accessing or we are just manipulating this top in a constant amount of time. Again, this push operation and pop operation, both of these operations take big O of one time. That is the constant amount of time. Similarly, if we check is our stack empty or not, we just check the value of this top. If this top is having any value other than -1, that means we have elements in the stack. So we return false. So again, this is empty operation, takes constant amount of time. Similarly, peek is nothing but it is similar to pop. Only thing is that we will not be removing or we will not be overwriting the top of the stack value. We will just see what is the top element. That is, if we are implementing it with the help of array, we will see that it can be implemented using arrays and linked list. So if we are implementing it with the help of array, as we have already covered it, and if we are implementing it linked list, we'll see both of these implementations one by one. So let's take an example wherein we are implementing it with the help of array. So what we will do, we'll just return this value. That's it. We will not be either removing it or overwriting this value. We'll be just returning the top of the element. So peek is similar to pop, but the only thing is that in pop we are removing the element. In this we are not removing the elements. Again, this will take a constant amount of time. So all these major operations are taking constant amount of time. That means with the help of this top iterator, we can do all these operations in a constant amount of time, because he is the guy who keeps track of what are the elements in the stack, and with the help of this we can remove the element from the top of the stack, we can add the element from on the top of the stack, we can push, we can pop, we can check if the stack is empty or not based on the value of this top, and we can also peek the element, right? We can take a peek of the element, right? So with the help of this top, okay? So again, that is in a constant amount of time. Now let's talk about the applications of stack. Now, whenever we use recursion, right? Whenever you use recursion, what happens internally, a stack is created, right? Let's suppose you have a function call, and in that function call, you are calling this function again. Obviously, this will be called from the main function, right? Let's suppose this is our main function. Let me just erase it and write it in. Yeah. So this is our main function, and it's calling this function, and this function is calling this function. That means it's calling itself again and again and again, unless and until a base condition is reached. Right now, once the base condition is reached, it starts popping it out. Right. This is all these are push operations. Right. And now pop is performed one by one, unless and until all the function call return its value, and finally it returns to our main function, and finally then main function is popped out of the stack. So whenever we are using recursion, a stack is maintained. And we also find out when we talk about recursion more in depth in this tutorial, we'll see how we to create this activation record that is created, and activation records are created, and with the help of these we can easily detect what are the statements that are yet to be executed, okay, in a function call. Let's suppose you have three statements in a program, and one of them is to check the base condition, second is to the function call itself, that is this function calling itself, this is a function outer function, and in that function you have three steps, and then this is a simple print statement, okay. Then let's suppose this is an activation record, and one, two, three. So this is checked, and this calls the function again. Again, an activation record is created. So again, one, two, and three are checked. So this is checked. Again, this calls a activation record. So now these are all push operations. So once it returns, now the pop is performed. Now it returns to this point and it executes this value. That is prints out the value, whatever is the value, and once it is done, so it returns to the function who called it, and once that is done, this will be popped out of the stack, and then once this is executed, it will return to the main function. So in recursion, stack is maintained internally. Now what about parsing? So whenever we talk about automata, right, automata is one of the subjects in computer science. Therein the parsing happens whenever your program is divided into tokens. Tokens are nothing but keywords. What are the keywords in this program? What are the conditional operators in this keyword? What are the constants? So all these in your program, all of these things are divided into tokens, and then parsing happens. Okay. What about the browser? Your application whenever you open up any website, right? Let's suppose you are opening Great Learning Academy. Before that, you go into the Google Chrome, you type in Great Learning, therein you will get the link of Great Learning Academy. Click on it, it redirects you to the Great Learning Academy. Then in Great Learning Academy, you look for the popular courses, or let's suppose IT and software courses. When you click on it, let's suppose it directs you to the another course that is related to IT and software. In that you have, let's suppose, C. You click on it and it will direct you to the C program. So one by one, these are all push operations: P1, P2, P3, and P4. All these are push operations. Now once you press back, what happens? You pop out, this pops out of the stack, and you go on to this courses. Again, you press back button, you go on to the Great Learning Academy. So these are all pop operations, and finally when you click on the back icon, you go on to the Google page, right? So this is all that happens while we are working in browsers and in editors. Whenever you do redo operation or undo operation, again a stack is maintained. So these are all the applications of stack. Now let's try to implement stack using arrays. Now before we do that, let's try to understand the declaration and initialization whenever we are implementing our stack using arrays. So we define a structure here and we named it stack, stack, okay? And in that stack structure, we have three data members. What are those data members? The top, which is used to access the top of the stack, which is used obviously for push and pop operations. Then we have the size of the array, and then we define the array. Now also, whenever we are going to create this array, we are going to call it in the main function. And in the main function, when we call this create method, we are sending the arguments, that is the size of the array. And in this we create, and we are returning, after that we are returning the stack. Okay, so how do you allocate memory to the stack? So we use malloc operation and we define the size according to this structure of the stack. And once the size is there, we just typecast the stack, that's it. And then we assign values to these data members, and we assign, for example, in this case, we assign the size to the size data member and top equal to -1 to this top of the stack. And then we allocate memory to the array with the help of malloc function. We allocate size to the array with the help of this size of, and according to what is the size of this int. Okay, so we allocate memory to the array and then we finally return the stack. So that is why you see the return type of this is struct stack pointer. Okay, so this is how you declare when you're dealing with array implementation. Now let's try to understand the implementation of push method in stack using arrays. So the first thing that you see in this push method is the array that we have passed and the item. So now let's suppose this is an array. I have written it in this way. So the element that we are going to push is obviously, let's suppose this is 5. Now we're going to push a 5. Now next time around we are going to push a 10. Now next time around we are going to push, let's suppose, 15. So we have a pointer that is pointing to -1 at the starting, and as soon as we are going to insert it, right, we're going to insert it, we're going to update our top, right? So it will be from -1 to 0. So that is what we are doing. So we have the stack, and in that stack we are going to insert this in array, and we are going to update first the pointer, that is this top that is present in the stack, right? And we're going to pre-increment it. First we're going to pre-increment it. That means in -1, from -1 it will first go to 0, and then we access this ARR of 0, right? And then we insert this item, that is 5, in that particular array. Similarly, when we next time around we're going to insert 10, we're going to pre-increment, because this time around the value of top is 0. The next time around we're going to increment it, which will be ARR of 1. We're going to store this. So top will be pointing to 1, then top will be pointing to 2, right? So it will be something like this. So we have 5, 10, and 15, and so on, right? This will be 0 to 0, 1, and 2. The top will be here. So let's suppose the size of this array is 4, and next time around when you're pushing, right, when you're pushing this another element in there, let's suppose 20, then it will be 3. So the next time around when you are inserting the element, right, when you are trying to insert this element, that is, let's suppose you are passing in 25 and you're trying to insert, but the occupancy of this array is full. So we check if is full, that if this stack is full or not. Yes, it is. Then we return from this function. Okay. So we will see how to implement this full method, but right now you can think of it as a pointer which does not allow us to go exceed the limit of this array in terms of storing the elements. Okay, so this is how you implement push using arrays. Okay, so now let's move ahead and try to implement pop. So now you have the stack available, right? Let's suppose you have the stack available, and the first element that is there top will be obviously pointing to this. So as if you can observe carefully the pointer that we are just updating, so whole operation, whole of this function is executed in constant amount of time because we are not traversing anything, we are just updating our top, that's it. Similarly, in pop we have the top that is pointing to the top element of the stack. So we need to keep this thing in mind that we operate this stack in last in first out manner. So the last element in was 20, right? And this will be the first element that is out. Okay. So top is pointing to this location. Let's suppose, let me name this as 3. Okay. So now what we are going to do, we are going to pick first, we are going to access this top. Okay, so the top will be 3. So ARR of 3. And then we are going to return that ARR of 3. So 20 has been returned. So that is why you see the return type of this pop as int, and we are passing in the array. Okay, as an argument. So 20 is returned, and we'll see what we are going to do with this. Maybe we will print it. Okay, so we're going to see what we are going to do with this 20. For now, let's suppose that we are going to print it. So we are printing this 20 in the main method, and we are then decrementing our top. So this is a post decrement. Okay, so we're going to decrement after this whole thing is O. So it is pointing to this. So this 20 will be still there. We are basically overriding it. Okay, so then top will be here at 2. So again, we are going to remove this. We are going to print 15 in the main. Then top will be pointing to 1. Then we are going to print 10. Then finally, we are going to print, we have top at 0th location, a 0th index. We are going to print 5 in the main method. Then top will be at -1 in the next step. Now, next time around, when we are trying to delete an element, but there is no element, we check if is empty condition. Obviously, we are checking it throughout when we are performing these operations, right? Whenever we are performing pop operation, we're going to check first this condition. So next time around, unless up to this case, we not what executing this if block, right? But we are simply returning the value with the help of this method, this statement. Okay. Now this time around, we check if this stack is empty. Yes, it is, right? At that time we return -1, and then maybe in the main method we signify if we have returned -1, then we can put a message that okay, we cannot delete any elements, the stack is empty. So this is how you implement your pop method. Now obviously there are two things, right? You need to see what how to implement is empty, and in the earlier push method you need to see how to implement is full. Now let's move ahead and see how to implement is full. So basically is full is used to keep the track. Okay, if top, whatever is at top, whatever is the current position of top when we are inserting the elements, if it is equal to the size -1, that is the actual size of this array. Obviously this array will have some size when we are declaring this and initializing this in the structure. Okay, at that time, let's suppose we have defined this array as 100. Now, the size -100 is 99 because we know indexing starts from 0. Now, if our top is at also 99th index and we are storing the element, so this time around, both of these are 99 and 99. This time around, these are equal. So we return true, obviously, right? So if this is full, we will return yes, it is full. So we will return true. Okay, so since both of these are equal, so we return true, and this in this case we return 1. Okay, so because we are returning, the return type is int, so we are returning 1, and later on in the main method we will do something. So this is the condition when 99 is equal to 99. In this case, when we have the array as 100, the size of the array is 100. So this time around we can easily detect or depict and say that okay, our array is full, we cannot insert any more elements. So this is the condition of this is full is condition of overflow. Okay, this is the condition when you check okay, is our array Full, yes it is. This is the condition and this condition is known as overflow. Okay. Now let's see how to implement is empty. So in this we are simply going to check if top is equal to -1. If top is equal to -1, that means we are not having any elements in the stack, and we are going to delete something from this. It is not possible because there are no elements. So if that is the case, we are going to return 1 and saying that okay, this is the function is empty is returning 1. That means the stack is empty, and we can put a message saying that okay, we cannot delete any elements. And this condition of is empty, and whenever you're trying to delete an element from an empty stack, and this condition is known as underflow. Okay, so now let's try to understand how to implement peak. So obviously when you talk about peak, we are not going to remove anything, or we are not going to override in this case. When we are talking about implementation using arrays, we are simply we have passed in the array and we are checking if this is empty, then peak is not possible, obviously, right? At that time we will returning this int min, which is the minimum value of the integer. Okay, so if there is an element in the stack, right, at that time what we are going to do, we're going to just return the value that is at the top of the stack. So we access the top, that is, let's suppose in this case, let's suppose this is at index 5. So we access ARR of 5, that is with the help of this stack operator, obviously stack variable. And we are going to return that value. So the return value is integer. So that is why you see the return type is integer. And we're not going to overwrite it. Still our top will be at this position because we are just taking a peek at the stack. Okay, we're just looking at which element is at the top of the stack. That's it. Okay, so we are going to return it and that's it. Okay, so now let's see how to implement these functions in code blocks. So now let's see the implementation of stack using arrays. So you have this structure over here, and in this you have top, that is used to, that's a pointer, and then the unsigned size of the array, and then we are going to have this array inside the structure. Done. And plus we have these libraries so that we don't have to explicitly create everything from the scratch. Okay, so then we are going to create this method which is used to create. We have already seen it in the declaration and initialization part, wherein we are just initializing the stack. We are just initializing our size, top, and the array with the size, and then finally we are returning the stack. So this create method is already covered. So then what happens in full, whenever we are checking if the size is full or not, if the array exceed whenever the size of the array is maximum, that is if the size of the array is 100 and we are at 99th location, the top is at 99th location, and obviously we check it with the size of the array, which is 99 because indexing starts from 0. If 99 is equal to 99, that means this is the full condition, our stack is full. Now if top is at -1, that means our stack is empty. So we can have this message printed. Okay, this empty. Right now we cannot delete anything from our stack because there is no element in the stack. So this is full and is empty are these two methods. Then we have this push method, wherein first we check if can we push an element in the stack or not. We check for the is full condition. If yes, then we insert the value, that is this item. And in pop, we will first check can we remove anything from the stack. We check is empty condition, because if there are no elements in the stack, we cannot delete anything, right? Then finally we have this method, peak method, wherein we are just peaking the first element in the stack, that is top of the stack, and that's it. We are not going to change the top, that is we are not going to change the top of the stack. It will remain as it is. Okay, we're just speaking. And then we have this main method. In this main method we are having this value which is used to insert the value in the stack, and then the n, which is our choice. Okay, so we are again going to create a menu, and in this menu we have push, pop, peak, is empty, exit, and then we are going to enter our choice. So if we picked anything from 1 to 5, then we are going to implement these functions one by one. So we have this scanf statement wherein you ask the user enter your choice. If you pressed 1, we are going to call the push function. If you press 2, we are going to call the pop function. If you pressed 3, we are going to call what is peak of the stack. We will call peak function. If we call, if we press 4, we are going to see is our stack empty or not. And finally, if you press 5, we are going to exit out of the program. And if there are no state, if you press something which is not which is not in this range from 1 to 5, right, including 1 and 5, then we have the default case wherein you will type, wherein you will get the output as wrong message, and then you will break out of the program. And then it will also prompt you a message wherein it asks you, do you want to continue or not? If you say Y, that means yes. If you press Y from the keyboard, it will still continue. Okay, so this is the menu that we have created. Okay, now let's minimize this also, and now let's try to run this program. So we'll do build and run, and this is our menu. Okay, so now in this, we first ask the user to enter his choice. Now let's suppose we pressed 1. Okay, now the user says, okay, we are going to push. So now let's suppose we are going to push 10. So this is a stack. Okay, do you want to continue? Press Y in lowercase. Okay, then again we are going to push, press 1. Do you want to, whatever is the value, let's suppose it is 20. So 20 is the top. Okay, we have 10, we have 20. This is a stack. Okay, do you want to continue? Yes. We are going to push into your choice. We are going to again push. Okay, and let's suppose this time around we are going to push 30. Okay, do you want to continue? Yes. Now we have 10, 20 and 30. Do you want to check the peak of the stack? Yes, it should be 30. So let's press your choice 3. You get top element as 30, which is right. Okay, now we are not removing it, we are just peaking it. Okay, so now if you want to check whether whether your stack is empty or not, what you're going to use, we are going to say yes. First we are going to say continue, and then we will check if our stack is empty or not. So we are going to call is empty function, and we'll say is it is 0, that means it is not, it is false. Okay, that 0 represents false. Okay, it is not empty because we have elements in the stack. Okay, so now let's pop the element. Since we have 10, 20, 30, so the element that we should be able to pop should be 30. So let's press 30, we should get but let's press 2 and we got 30. Again, let's pop the element. And this time around again let's pop. Okay, enter your choice, let's pop. We will get, this time around we will get 20. Yes, correct. Okay, now the last pop, and we press 2, we get 10. Now, yeah, would you want to continue? Yes. Now this time around, let's see, is our stack empty or not? Let's press 4. Yes, we got true. Our stack is empty. Okay, so this is how you play around this. And now if you want to exit, you can press 5, or if you press anything that is there apart from Y, it will just break out of the loop. Okay, this is how break out the switch case. Okay, so that we are done with this implementation. So in this way, we have just implemented all the functions that were there, right? First we implemented what, push, then we implemented pop, then we implemented is empty, then we implemented what is empty and is full, then we saw peak. Okay, with this we implemented all these functions using C in code blocks. Now let's try to understand the implementation of stack using linked list. Now before we do that, let's try to understand the declaration and initialization when we are implementing a stack using linked list. So we create a node obviously, and that node will contain two things. What are those two things? The data and the next. Now this next will be nothing but the pointer which is pointing to the node, that is the next node. Obviously it will be of the type node. So this is why this is a self-referencing pointer, because it is pointing to something which is of same type as it is. Okay, and plus we have the data part wherein we enter our data. Plus we have this variable which is of type struct, which is of type node. And finally, what we do, we create this temporary node. Let's suppose we are creating this node here. In this case, right, let's name it tmp. And then what we are doing, with the help of malloc, we are allocating memory, and we are obviously calculating the size and then locating memory and then typecasting it. And then we are inserting the value as 5, and then the next part of it, which is this. This is the next part, and this is the data part. And then what we are doing, we are locating null to this, because there is no node which this particular node is pointing. Okay, so that is why it is null. So this is how you declare and initialize your node while you're implementing stack using linked list. Now let's try to understand push implementation using linked list in stack. So if you can see that this push method, we are passing in the argument as the element that we want to push. Now, before moving into the implementation, one thing should be clear that whenever we are implementing push, right, in any either in arrays or in linked list, one thing that we have to keep in mind that this push operation should take constant amount of time. Now in linked list, we have already seen that if we want to insert at the end, right, we let's suppose we have this set of elements, let's suppose 10, 20, 30, 40, and 50. Now we want to insert this in a stack. If we insert it in such a way that we are inserting 10, then after that we are inserting 20 in a linked list, right? 30, then 40, then 50. Now to insert this 50, we are taking how many, we are traversing through all these elements and then pushing it at the end, which is nothing but insertion at the end, right? When we talk about when we talk about insertion in a linked list, we have already seen this insertion at the end and insertion at the beginning, right? So if we use this insertion at the end, we are traversing through all the elements and we are implementing this push function in a linear time, that is big O of n, which is not correct. So in order to use the linked list implementation, we need to implement this push in a constant amount of time, which can be done when we use insertion at beginning. Insertion at beginning. Okay, so let's clear the screen and let's see how it's done. So we have this element in place. We have called this push function in the main method, that is our driver method. And then what we have done, we have created a node, right, with the help of malloc. And now what we are doing, we are inserting data in the element, we are inserting element in the data part of the node. So this is tmp, and obviously this will have some address, that suppose that is 1000. Okay, so now what we are doing, we are storing the element which is 10. Okay, now again, whenever we are inserting an element at the beginning, two cases are there, right? We have already seen them. First, that we have no element in the linked list, that is our header or head node is at head, that is the pointer that is pointing to the first node is null, or it is having some address. It can be one node or multiple nodes, it doesn't matter. Okay, so in this case, let's suppose that there is no node. At that time, p will be null, that is our head, so it will be null. P is the head and it is null. So then what we will do, we'll just update our p to temp. So p is now this temp, and that's it. Okay, and we are also inserting, we are also initializing this next part to null because there are no such nodes. Okay, so we have inserted, we have implemented this push operation in a constant amount of time. Done. Now what if there are multiple nodes? Okay, let's clear out the screen, and there are multiple nodes. Let's suppose there are two nodes already, and one is containing 10, and this is 20, and this is 1000. The address, this is 2000, and p is pointing to this, that is our head node, and this will contain 2000, and this is null. So this is our linked list that is already present. Now we want to implement push operation. If we insert here, this is not correct because it will take big of n time. Now we want to insert something that is at the beginning. So we will check, okay, we first create the node, that is this. We create it with the help of this malloc function. We allocated its memory, and then we inserted the data. Let's suppose data is 5 and we have address as 5000. Okay, so this is our temp. So what we did, we insert the value. So these two steps are done. Then we check if p is null. No, is p is not null. This will not be executed. Then what we'll do, we'll check, we'll insert the value in temps next as p. So temps next is this, which is right now empty, and we will insert p in it. So p is 1000. So here you have your link. Okay, so this is insertion at the beginning in a constant amount of time. Okay, so push is implemented in a constant amount of time. Now after that, what we do, we'll just update our p, that is our update our head, and it is pointing to the first node. Done. So this is how you implement push operation using linked list, which is nothing but insertion. Insert your element at the beginning, okay, because it takes constant amount of time, and we need to keep this push operation in constant, or implement this push operation in constant amount of time. Now let's try to understand implementation of pop method in stack using linked list. So we have already seen that when we want to delete an element from, or when we want to delete a node from linked list, we have two operations, right? Insertion, or we can say not insertion, deletion, right? Deletion at beginning and deletion at the end. Now, since we want to perform this operation in a constant amount of time, so deletion at end is out of the picture. Why? Because if we are deleting the node at the end, we need to traverse all these nodes to reach here, which takes big of n time in worst case scenario, right? So this is out of the picture. Now we will be implementing this pop method using the same approach that we did in deletion at beginning. So let's see how to do it. So the scenario remains same. We are not going to change our head node, that will remain as it is. So there are again two cases: null, when we cannot delete an element and or the node, and wherein we can delete the node, that is the first node. Okay, and always we will delete the first node. Okay, so when we talk about this first case, when we don't have any elements, right, and there are no nodes in the linked list, that will be the case of underflow, right? We are trying to delete an element in the linked list when we don't have any element in the linked list or any node in the linked list. That is not possible. So if p is null, that is if our head is null, we can print no element to be deleted. There is no element that we can delete. Now if p is not null, that means head or p is pointing to this node, that means 1000, let's suppose. So at that time what we are going to do, we are just going to put, or we can just update our p to p's next, which is nothing but this node. That will be, let's suppose, 2000 here. So p will be pointing to this. That's it, we have removed this. Okay, this is how you delete or perform pop operation in stack. Okay, and obviously if we are changing, or we can use this temp when we have to traverse. Okay, so this is how you implement pop using what linked list. Now let's try to understand is full. So now think about it in this way, right? In arrays, when we implemented this is full method, we were looking at the size of the array, right? If size of the array is 99, if size of the array is 100, and the last element will be stored at 99, right? Because indexing starts from 0. So we were checking if 99 is equal to the wherein the top is also at 99. So this is a condition of overflow. Now when we talk about linked list, this overflow is present only in arrays because of the fixed size, that is the nature of the array. We have to define a size and it is having a fixed size. This overflow condition is possible only in that case, right? Because if we talk about linked list, right, since it is dynamic in nature, we can add as many nodes as we want, as we have, as our application grows, or if we want to insert many elements, right? So is full condition is not applicable when we are implementing stack using linked list. Now what about is empty? Yes, this will be the scenario, right? If our stack is empty, right, that means if there are no nodes available in the linked list, at that time p will be equal to null. So we'll say stack is empty, else we will say our stack is not empty. That's it. Okay, let's move ahead. If we want to peek the element, right, if we want to take a peek at the element that is present at the first, that is present at the head node, or we can say the p node. So we are just peeking at the top of the stack, right, that we just saw in the array implementation as well. So we are just looking at this, so we just print whatever is in the heads data. That is what is peek, right? This is the first element, this is the top of the stack, right, this first element, because we are implementing it insertion at beginning, like we did in that, right? So just like we implemented insertion at beginning, we have our top at this location, that is at the first, and again this will be a constant operation, right? So we are just looking at the top of the stack, that is head nodes next or p nodes data. That's it. If there is an element, there will be this is the case wherein the stack is not empty, and if there is no if our stack is empty, that means if p is null, right? If p is null, at that time we will return -1. That's it. Okay, and you can just use this condition, or you can just implement it in a different way, just by returning if p is null, then you return -1 or anything like that. Else you can say that if stack is empty, then you return 0, else return 1, or the vice versa. If you want to say that is stack empty true, you return 1, or else return 0 instead of these printf statements. Okay, it depends on implementation. Okay, so this is your peak operation, and this is also happening in a constant amount of time. Now, if you want to display all the elements that are present in the linked list, this is similar to what we have already seen. So you have this temporary variable because you don't want to change the head node, that is p. So you have this temp also pointing to the head. Then you will traverse one by one. You print out the data that is there. So you will be printing out the stack that is there, right? The top of the stack is this 10, then 20, then 30, then 40, then 50. So you will represent this in this manner. So this top is the top of the stack. Okay, so this is how you display your elements. Now let's see the implementation of all these methods in code blocks using C. So now we have a structure that is data and the next, because we are implementing it using linked list, right? So we have these set of temporary variables that we will be using, and we are declaring it globally so that we don't have to pass every time. So we have this method, right? Insert is there and delete is there. Let's just write this again. So let's just save these files. So these are few methods that we will be implementing: insert, display, delete, and is empty. Okay, done. Then we have, let's minimize this as well. So then we have our driver function, that is our main function. We have this menu in place wherein we are going to use push, pop, is empty, display, and exit, and we will enter our choice. We'll ask the user to enter his choice, and we will be storing it in n. So this is why we have declared this n over here. Then the value is for inserting the value. So this is the head node, which is null. Okay, this p. We have in switch place that takes an n as an argument, which is nothing but the choice, and 1 represents, if you press 1, that means you will be entering value inside the stack, and you will just ask the user to enter that value. So we have used that val which we declared earlier over here. Okay, then we pass in this to an insert, which is nothing but insertion at beginning, and the same, the delete function gets called, which is nothing but deletion at beginning, because we want to perform all these operations in a constant amount of time. Then we have case 3, which is for empty, to check if the stack is empty or not. Then we have this display method over here to display all the elements. Then exit, to exit will be exiting from the program, and if we enter anything apart from 1 to 5, that will be wrong choice and we will break out of the program. And we will also prompt the user the message, do you want to continue or not? If he says Y, that means he presses Y in his key on his keyboard, then we will continue. Else if he press anything apart from that Y, we'll get out of the program. Okay, we have this insert function over here, which is nothing but insertion at beginning, wherein we will check both these cases, wherein if p is equal to null, that is if there are no elements in the stack, yes, you can see it in the stack or in the linked list. Else we will traverse and we will update our this head node. Okay, it's because this is insertion at beginning, right? Done. And we also pass the element that we want to insert. Then deletion, again same thing, we will print the data. Else we will print, if the underflow condition is there, we will print that no data is there is no element in the stack. Then is empty, we are just checking if the stack is empty. We are using this implementation where p is equal to null, and if that is equal to null, then we say stack is empty, else stack is not empty. Then display function, we are traversing through the linked list, and that's it. Okay, one by one using this temporary variable temp. Okay, done. So these are few methods, and this is our driver method. Okay, now let's run this program. Let's build and run this. So you see we have our menu in place, and now it is asking for the user to enter his choice. Okay, so let's say we want to push the element. Okay, we pressed 1. Now which element do you want to push? Because this will be the last element in the stack. Let's suppose we are pushing 40. Now he says, do you want to continue? Yes, press Y. Okay, then again we want to push it. Okay, we want to push another element. Let's suppose 30. Okay, and then we want to continue. Yes, then again we want to push, press 1, and then we want to push 20. Do you want to continue? Yes, we want to continue. We are going to push again. And this time around, we push 10. Now, do you want to continue? Yes. Okay. So now what is happening? 40, then about 30, 20, and 10. So we have a stack in which 10 is the top element. Okay. Now, if we want to pop, what should be, what is the element that we should be able to pop is the 10. Now, let's see. We press 2, we should get the output as 10. We got the output, element is deleted, that is 10. Okay, now we want to check if the stack is empty, since there are elements, right, 20, 30 and 40 in the stack, 20, 30, 40 in this manner. So we want to check if this is if there is if the stack is empty or not. So let's say 3, let's enter the choice 3. He says stack is not empty, which is absolutely correct. So let's press Y and say continue, and now let's try to pop again. So 20 is deleted, and now finally let's try to display all the elements. So 10 was earlier there, we popped it. 20 was there, we popped it. So now we are left with what, 30 and 40. Okay, so 30, 40 should be printed, okay, in the form of stack. Okay, now let's try to display that. Let's see 4, let's press enter. So 30, 40 is the stack. Do you want to continue? Yes. Now let's press 5 to exit our program. Press 5 and we are out of the program. Press any key to continue so that we are out of this prompt. Okay, done. So now let's go back. So in this way, we implemented push, we implemented pop, we implemented is empty, and we implemented push, pop was there, is empty was there. We implemented display. Okay, so these are some functions that we implemented in the code blocks using C. Is it possible, once more I will ask you this question, is it possible for us to have is full condition in linked list? No, because of its dynamic nature, that the size is dynamic. So this condition, overflow condition, will never be there, but underflow will still remain. That is nothing but if you want to delete an element but the stack is empty, or you don't have anything in the linked list. Okay, now let's talk about the advantages and disadvantages of stack. If you talk about advantages, it maintains data in a LIFO order, right? The data is maintained in a LIFO order. That means the last element that is there in the stack is readily available for us to use. So one of the readily available, right? So one of the applications of using stack is it can be used to evaluate expressions, right? Therein we require this feature, that is LIFO, right? And all the operations that are performed in stack, like push, pop, and then is empty, and then pick. All these operations take constant amount of time, which is very important while you're playing around with competitive programming, or while you're doing competitive programming. At that time, these are very important that you program in the most efficient way. Programming in most efficient way is important, and it is very crucial for your selection, right, in competitive programming. So all the since all the operations are performed in a constant amount of time, so these the stack is used oftenly when you are doing competitive programming. The disadvantages, since we are restricted, right, there's a restriction that we can only add and remove elements from top of the stack. So this is one restriction that is there. Thus it is not very much flexible, right? It is not flexible. If you talk about the flexibility of how we are storing data in the stack, it's not very much flexible. So these are the disadvantages of using stack. Now let's try to understand queue linear data structure. What is queue? Queue is a linear data structure. That means all the elements in the queue are stored in linear fashion. Now it follows a principle of FIFO. That means there's a restriction that whatever is the first item in is the first item that is to be out. Okay, so now let's try to make a queue. And let's suppose you are in a queue and you're waiting for a movie. You're waiting for a movie ticket to buy. Okay, so there is one person, then there is another person, right? So these are few persons here, right? And you're waiting in a queue. So now the first person who is in the queue will be the first person who will get his ticket, right? Makes sense, right? So he will be the guy who will get his movie ticket first, and he will be out of the queue. Then the next person who is in the queue is the next person who will get his tickets, right? And let's suppose a new person comes in, he's not going to go ahead from this person, rather he is going to go behind this person. Then the next person comes, he will go after this person, and in the same way. So this is nothing but a FIFO principle. Okay, the first person in is the first person out. Okay, now insertion will always take place from the rear end. Okay, and if you talk about deletion, it will always take place from the front end. Okay, so this is our front end and this is our rear. Cool. So for examples, buying the tickets from the counter, or it can be a movie ticket, or it can be a bus station. You are in front of a bus station trying to get tickets for your bus, right? These are some examples. Now there are four major operations when you talk about queue. What are those major operations? So NQ. So you are going to insert an element in the queue. This is what you mean by NQ. DQ, you are going to delete an element, okay, from the queue. Then peek first, that you're going to peek the first element that is in the queue. And peek last means that you're going to peek the last element that is in the queue. So you will have two pointers. One is front and another is rear. And with the help of these pointers, you're going to NQ, DQ, peek first, peek last. You're going to perform these operations. Now, one major advantage of these operations, these four operations, is that all of these operations are performed in a constant amount of time. That means the time complexity of performing these operations is O of 1. So that is why when you talk about competitive programming, Q is most commonly used data structure because of these things, right? Because of its time complexity, right? You're able to perform your operations in a constant amount of time. Now let's talk about applications of queue. So it is used in scheduling algorithms of the operating system, like first in, first out scheduling algorithm is there, round robin is there, and we have multi-level queue that is there. In all these algorithms, queue is used, okay, for storing the data or the processes. It's also used in maintaining playlists. Like when you have a playlist, let's suppose you have 10 songs in a queue, right? And after one song, the next song which is in the queue will be played, and it goes on for like this, right? So for maintaining a playlist, again, a queue is used. It's also used in interrupt handling. Let me take an example here. You know the process state diagram of operating system. So it is also used at that time. So when you have an interrupt and therein if your process is being executed at that time, that process is preempted out and it is stored in a queue. Now the next time when this priority or this interrupt is handled, once it is done, then it starts picking up the process which was in the queue and starts executing that. In the meanwhile, if there are some other processes, that those processes will also be in the queue. So a queue is maintained, and once the interrupt is handled, they will start taking out that process that was being executed earlier and executes it and completes its execution and terminates the process. So it is also used in interrupt handling. Now let's try to implement queue using arrays. So let's first see the declaration and initialization using arrays. So we have defined a structure here and named it queue. And in this structure, we have three data members of type integer. That is, first is friend for keeping the track of the friend and from which we will delete our elements. And there is rear from which, with the help of which we can insert the elements in the queue. Then there is size of the array. Obviously, we are implementing it with the help of array. So we will be having the size. So we have then unsigned actual size of the array, right? This is the actual size of the array, and this is the size wherein we will keep the track of how many elements are there in the array. Then we have the array, okay? And then this is our structure, okay? Then how would we create? We will call this create queue method from our driver method. Driver method means the main method. And therein we will pass the actual size of the array. And then we will allocate size or allocate memory to the queue with the help of malloc function, wherein we calculate first the size of the structure, which is this queue, right? Once we are done with that, then we will typecast it in the C. and then we will assign this to Q. Then what we will do, we'll assign the actual size to the Q. Then we will initialize our friend to the size of the queue, which is equal to 0. Right now, there are no elements in the queue, so the size of the queue is 0. That means the front will be at the starting, which is 0th index, right? And then what we will do, we will assign the value to the rear side, which is actual size of the array. Let's suppose the size of the array is 100 and we are subtracting 1 because indexing starts from 0. So our rear is initialized, our front is initialized, our actual size of the queue is also initialized. Then we allocate memory to the array. Again, we will calculate the size with the help of size of operator and then allocate memory and then typecast it to the type integer. And then finally what we do, we'll return this queue. So this is the declaration and initialization when we are implementing queue with the help of array. Now let's try to implement queue using linked list. First, we will understand the declaration and initialization. So obviously we are using linked list, so there should be a structure of the node, right? So we are defining a structure that is of the node. And herein we will have two data members. One is the data part and another is the next. With this next is used to store the addresses, right? This stores the address of the next node that is connected to it, which will be obviously of type node. So that is why we have this struct node, which is this next is a self-referencing pointer because this next is also pointing to the node, which is of type node. And plus we have the data part wherein we are going to store our integer values. Plus we have this temporary variable, which is of type node. Plus what we will do, we will allocate the memory with the help of this malloc function and we calculate the size of the node, that is the structured node. And then we typecast it and then this temp will be pointing to something like this. This will be the node and it is named as temp and it will have some address, let's suppose 1000, and this will have data part and the next part. Now we are allocating or we are assigning 5 to the data part, that is this 5, and we are assigning null to the next part. So this is our node and this is currently temp is pointing to this node. Okay. So in this way, we understood the declaration and initialization of linked list and how we are going to implement queue using linked list. Now let's try to understand the implementation of enqueue operation in a queue using arrays. So this is an enqueue function that we have over here. And in this we have passed in the array and the item that we want to insert. Now before we move on to this enqueue, let's try to understand what this enqueue operation is. It is nothing but if you want to insert an element in the queue, right? And right now we are implementing it using arrays. So we want to insert an element. That operation is known as enqueue, and we need to keep this thing in mind that we perform this operation in a constant amount of time. Now let's try to understand what is this enqueue operation. So first we are going to check if the queue is full or not. Now why this condition is important? Because this is the condition of overflow. That means we want to check if the array, let's suppose we have this array and the last index is 99. That means it starts from 0 to 99. That means the size of the array is 100. Now we want to check if the queue that we have created is full or not. So we check if the elements that are present in the queue is equal to this 99. That means the actual size of the queue and the actual size of the array are these equal. At that time we cannot insert any more item in the queue. So this is the condition of overflow. Now let's see what is the next thing that we are doing. So since both of these front and rear are at -1, as we have seen in the declaration and initialization part, right? So this is the 0th index and now this is the array, and let's suppose the last index is 99. So now when we are trying to insert an item in this array, the first thing that we are going to do, we are going to, obviously the enqueue will take place from the rear end. So we are going to update the rear. So now rear will be pointing to this index 0 and we inserted this element in the array, that is this item that we inserted in this queue is 5. Let's suppose we passed in 5. So 5 is inserted, right? Now these two steps are done. And this condition is false because our queue is right now empty. Then what we are doing, we are now this helps us to keep the track of the number of items that are there in this queue, because we are removing, and then we also want to keep the track, since this size helps us to keep the track. Let's suppose we are over here and this is the 50th index, so we want to keep the track. Okay, still we can insert elements that are less than, obviously the index is 50 right now, the size is 50, and we can insert elements up to 99 size. Okay, so this helps us to keep the track of that. So this is the actual size, this is the actual size of the queue, and this that actual size of, then that is different. Okay, this size is actual size of queue, and when we pass in the actual size, that is the size of the array. Okay, these two are different things. Then what we are doing now, since when we are inserting the element first time, at that time we want to update the front as well, because front is the guy who is responsible for deletion. So we want to keep him in track, that okay, once we have inserted the first element, we want to update him. Okay, this is the first point where this is the point from which you can start deleting the in the queue. Okay, you can start deletion. So at that time, if it is at -1, we'll update it. Okay, the front is also at this position, that is 0th index. So both front and rear are at 0. Okay, when the queue was empty, and then we printed out this item. Okay, we have inserted this item, that is 5, in the queue. Now let's suppose we are doing it the second time. Now let's suppose we have this 5 inserted and front and rear are both at this 0th index. Now the next time, is our queue empty? No, it is not. Now what we are going to do, we are going to update our rear. Now rear will be pointing to this index, that is 1. And then we insert the item. Let's suppose we are trying to insert 10. We have inserted the item, so these two steps are also done. Then we update our size, that is earlier size was 1 and now size is 2. So obviously the array size will remain the same, that is 99. Okay, not the 99 but 0 plus 9, that means the size, actual size of the array is 100 in this case. Okay, so now q is not -1, so we're not going to, the friend is not equal to -1, because now friend, earlier we updated it and friend was 0, since friend is binding to the 0th index. So we are not going to update our friend, because this only takes place when we are inserting element in the array, in the queue, or you can say the array implementation, right? We are inserting that element in the queue the first time, for the first time. Okay, at that time this condition, this if will be executed. Okay, done. Then we print out the item, that is 10 was enqueued in the queue. Done. So this is the implementation of enqueue. Now let's see the implementation of dequeue. Now dequeue, now one more thing before we shift to dequeue, one more thing that is there. So this is done, this whole operation is done in constant amount of time. Why? Because we have the track of both of these indexes, right? So obviously front is not required right now, but rear is updating all the time, and we have direct access to this memory location. That means we only require a single unit of operation. That is for the same reason the enqueue operation is executed in a constant amount of time. Okay, now let's move ahead and see the dequeue. So dequeue is used for, or this operation is known as deletion in the queue. Okay, now we have already placed our friend. Now let's see what are the things that we are going to implement in this dequeue method. So obviously we are going to pass the array, right? Let's suppose we have this array. We will take care of both the conditions when both front and rear are at this position, and then when front is at this position and rear is somewhere, and also when our array is empty. Okay, then at that time both front and rear are at -1. Okay, done. So now obviously we will be returning the item that we have deleted. Okay, so now let's first check if this condition holds or not. So we are going to check is empty condition. That means if this is the scenario at that time, we are going to return int minimum. That is the minimum value of integer. Okay, or you can return any arbitrary value. Okay, so this condition is checked, right? This case is checked. Now after that, what we are going to do, we are going, now we know for the fact that there is at least one or more than one item in the queue. Okay, so now we can delete, we can perform deletion. So the next thing is that we are going to pick the element with the help of this friend operator and insert it into this item, that is the temporary value we are using. So let's suppose 10 is here and 10 is here. Okay, and then we have 20, then we have 30. Okay, done. So in either of these cases, this case 1, case 2, case 3 is solved, right? So case 1 or case 2, what we are going to do, we are going to pick the element that is present at index 0 or at index that is friend. The index that is present in the friend is the element we are going to pick and insert it or store its value in this item, okay, so that we can return it. Okay, that's the for this purpose. Okay, so now if front and rear are at equal positions, that means in this case is happened, right? That means there is no further item in the queue, because it is obvious, right? Since front and rear are at this position, that means there is only single item in the queue. Done. So what we will do, we'll update our front and rear port to -1. That means this case, okay, when our item or when there were no items in the queue. Done. So we updated it. Done. Now, what if this is not the case? What if this is the case, right? Let's suppose rear is here. Okay, 40. So now if that is the case, what we are going to do, we are just going to update our front to this position. That's it. And also reduce in any of these cases, right, except for this one, we are going to reduce the size, because this is if block, this is else block, and this is executed anyways, right? Either this case is executed or this case is executed. This case is entirely different. This is done by this if, right? Now, if in any of these cases, we are going to execute this queue size and queue size -1. That means we will be reducing the size of the queue. Earlier, we had 4 items. In this case, we had 4 items in the size. That means size is 4. Now we have 3 items. So because 1 item is removed. Okay. In this case, we are also having 1 item in the queue. That means size was 1. Now it is 0. We are decrementing. Okay. This is how you perform dequeue operation. Now, one more thing is that since we have the pointer that is front, which is pointing to the index that or pointing to the element that we want to delete. So again, this operation is performed in a constant amount of time. That is, the time complexity in the worst case is big O of 1. That is constant. Now let's see is full condition. That is the overflow condition, right? That we checked while inserting the element. So now if the queue size, that is the size of the queue, which helps us to keep the track of the elements that are present in the queue, if that size is equal to the actual size, right, that 100, the actual size of the array, it is equal to the size that we have, right, that is used to keep the track of the elements that are present there, right? If this is the case, that means we cannot insert any elements any further. We cannot insert any elements, right? Or it should be something like, or it depends upon the implementation. What have you returned? If you have inserted 99, so because indexing starts from 0, so it will be somewhere around 99 is equal to 99, because indexing starts from 0, not 100. Okay, because 0 to 99 is again 100 elements. Okay, so now what we are going to do, if this is the case, that means we cannot insert any value in the queue. This is the overflow condition, and our queue is full. Done. This is the is flow implementation, and obviously we are returning then either 0, that means the stack is not full, or if the stack is full, we will be returning 1. That's it. Okay, since the return type of this method is int. Again, if you see, this operation is performed in a constant amount of time. Now, if you want to see if your queue is empty or not, that is simple. You just check the size of the queue. That is the elements that are present in the queue, not the actual size. If that is 0, that means if size is 0, that means your queue is empty. And what we are going to return, if that is the case, you're going to return 1, else you're going to return 0. Okay, done. This is again performed in a constant amount of time, that is big O of 1. Now, what if you want to get the front element, that is the front element of the queue? This is the front and this is the rear. So it is quite obvious that you have the tracker, or the front is the pointer that is used to keep the track of the front element, and rear is the tracker or pointer that is used to keep the track of the last element. So this is the first element that is there, and this is the last element that is there. So we have these pointers available. So again, these operations will be performed in a constant amount of time, and it is simple, right? If you want to see the front, first you check if your queue is empty. If it's empty, then there will be no front element, else we are going to just return whatever is at this position, that is with the help of this front iterator or pointer. Okay, then we are just returning that value, so it will be integer. Or if the queue is empty, at that time we will return the minimum value of integer. Okay, in any ways, both of these, either this return or this return, are sending the integer value. Okay, again, it is performed in a constant amount of time. Similarly, we can execute, or we can have this function that is get rear. Again, we will be having this pointer that is pointing to the last element, and we will be straight away returning that value. Again, it will be an integer, and plus we are going to check if, again, we are going to check the is empty condition to see if there are elements in the queue. Only then we will return the last element. Okay, again, this minimum is nothing but the minimum value of the integer. Okay, if you observe carefully, again, since we have the access to this rear pointer, that is the last element is available to us, right? With the help of this rear pointer, again, this will be performed in a constant amount of time. Now let's look at the implementation of these methods in the coding blocks. Now let's see its the implementation. We have these libraries in place which I used, okay, and then we define the structure as we have declared, as I have already taught you this thing, that the declaration and initialization part, wherein we have these three pointers, front, rear, and size. This size is the size of the queue, and this is the actual size of the array. Then we have the array. So this is our structure of queue. Then we have this method create queue, wherein we are passing the actual size of the array. Okay, and then we initialize our queue with the help of this malloc function. We allocate memory, then we update our actual size of the queue, that is the actual size of the array, and we are updating our actual size. Okay, then our elements that are present in the queue are right now 0 because there are no elements in the queue. We update our rear and front pointer, we initialize our array and allocate memory according to the size that we have received in the actual size, and with the help of size of operator, we calculate the size of each byte or each integer that we have in this queue, and then we typecast it to the integer. So this is the create queue method, and then we return the queue. Done. So is full is simple, that we check the size of the queue and the actual size of the array. Done. This is our is full, and we will return 0 or 1. This is done. This is also done. Okay, now let's see our enqueue, which means we will be inserting value. So we need to have one item here. Obviously we'll be checking first the overflow condition, and then we update our rear, because rear is the guy who helps us to insert the values, right? So we'll be inserting from the rear end. Then we insert the item, right? And then we check, then we update our size, because we want to keep the track of the elements that are present in the queue. Obviously the actual size will remain the same. Okay, and then if it is the first element in the queue, then we also update, at that time we update the front pointer as well, and then we prompt a message that enqueue to queue is this item, let's suppose 5. Okay, done. Then we check is empty condition, which is this size is helping us to keep the track of the items that are present in the queue. So if that is 0, that means there are no elements in the queue, right? And we return either 0 or 1 depending on that. Then we have the dequeue method, and in this we return the value. So first we check the underflow condition. That means if there are no items in the queue, at that time we cannot delete anything from the queue. Then what we do, we with the help of front, because that is the guy who helps us, or that this is the pointer which helps us to remove an element. So we pick up the element and put it in a variable that is item, and then what we do, we check if this is the only element that is present in the queue, right? If that is the case, then we update both front and rear to -1. Else what we do, we will see, okay, there are multiple elements in the queue, so at that time we will only update our front. In either of these cases, the size is reduced, so we and at the end we reduce the elements that are present in the queue, that is size minus 1. We decrement it by 1, and then we return the item which we have stored in over here, right? The item. Done. And then we have get rear and get friend. So basically we will be returning the values that are present, the first element that is with the help of this friend, and the last element that is present with the help of this rear methods. Okay, friend and rear. Then we have this driver function, wherein we have this value that we want to insert in the queue, and the n is the choice. Okay, then we call this create queue, and the size of the array is 1000. Then we define this menu, okay, over here, that is our menu. And in this, if we press 1, 2 and 3, 4, 5, 6 and 7, if we press any of these, what we are going to do, if 1 is pressed, enqueue, dequeue is pressed when dequeue is called when 2 is pressed, 3 is for is empty, 4 is for is full. When we want to check the first element in the array, that is 5, the last is 6, and then if we want to exit, we need to press 7. Else, if any of these values, that is from 1 to 7, is not pressed, we will prompt a message that this is the wrong choice, please re-enter. Okay, so now what we also prompt the user that please enter your choice, right? From 1 to 7 he enters something that is stored in the end. And then we have the switch case, wherein depending on 1, if 1 is pressed, we call what, enqueue. If 2 is pressed, we call dequeue. If 3 is pressed, we call is empty. 4 is pressed, we call is full method. 5 is pressed, we call friend. 6 is pressed, we call rear. And finally, if 7 is pressed, we will exit out, or we will break out of the program. And if any of these values are not pressed, we'll prompt a message that is wrong choice. And then we also prompt a message, do you want to continue? If Y is pressed, that means yes, that means we will continue, else we will break out of the program. Now let's try to run this code and at the same time build it also. So we have this menu in place. Now let's try to enter some values. So he's saying that enter your choice. Let's suppose we want to enqueue. We press 1. Then we enter the value, that is 10 in the queue. So it gets the message is prompted 10 enqueued in the queue. Do you want to continue? Press Y. Yes, we want to continue. Press again 1 because we want to again enter value. So we enter 20. Okay, 20 is enqueued. We press Y. We again want to enqueue and we press 30. Okay, now do you want to continue? Yes. So if you think of how many elements are there, there are 10, 20 and 30 in the queue. Now let's see if our queue is empty or not. Let's call these functions. Let's see if queue is empty, it will return 0, right? So we'll press 3 to check it. It gives the output as is empty 0. That means there are elements in the queue. Do you want to continue? Yes. Again, we press is full. We check is our queue full. Obviously, the size of the array is 1000, so we haven't entered those many values, right? So is full will also return 0. Do you want to continue? Yes. Now let's see. First, try to dequeue. So we press 2. So now earlier it was 10, 20, and 30. So we dequeued 10. So 10 will not be the first element anymore. So let's try to enter 2. So element is dequeued. Okay. Now let's continue again. Now let's see the first element. It should not be 10 because 10 has been already removed. It should be 20. So we press 5. We have 20. That is the first element. Now let's check the last element that is there, which is 6. Our choice should be 6. So the last element is obviously 30. So earlier it was 10, 20, 30. We removed 10. Then 20 is our first element. 30 is our last element. Do you want to continue? I will press any other key apart from Y. So I pressed U. So then I pressed enter. So we are out of the program. Done. So in this way, we implemented all of these operations, and all of these operations which were in queue, that is insert in the queue. Then we pressed dequeue. We implemented dequeue. Then there was get rear, get front. That is for the first and the last element. This is for the first to check the last element in the array, and this is for checking the first element in the array. We also went through some other functions as well. Those were, if we want to see is full condition, that is the overflow condition. This was the overflow condition to check is full, and also is empty. This is used when we were trying to remove and there were no elements in there in the queue, right? This is the underflow condition. So we implemented all of these methods, and all of these methods were implemented in a constant amount of time. That is the beauty of queue. Now let's try to implement queue using linked list. First, we will understand the declaration and initialization. So obviously we are using linked list, so there should be a structure of the node, right? So we are defining a structure that is of the node, and herein we will have two data members. One is the data part and another is the next. With this next can is used to store the addresses, right? This stores the address of the next node that is connected to it, which will be obviously of type node. So that is why we have this struct node, which is this next is a self-referencing pointer, because this next is also pointing to the node, which is of type node. And plus we have the data part wherein we are going to store our integer values. Plus we have this temporary variable, which is of type node. Plus what we will do, we will allocate the memory with the help of this malloc function, and we calculate the size of the node, that is the structured node. And then we typecast it, and then this temp will be pointing to something like this. This will be the node and it is named as temp, and it will have some address, let's suppose 1000, and this will have data part and the next part. Now we are allocating, or we are assigning 5 to the data part, that is this 5, and we are assigning null to the next part. So this is our node, and this is currently temp is pointing to this node. Okay. So in this way, we understood the declaration and initialization of linked list and how we are going to implement queue using linked list. Now let's try to understand the implementation of enqueue operation using linked list. So again, I'll reiterate what I said when we did the array implementation of enqueue. Again, we are going to implement the enqueue operation, but this time around we are going to use linked list. Now, keeping this thing in mind that this operation should be executed in a constant amount of time. Now, as we have already seen in the linked list part, right, wherein we did something that is known as insertion at the end. So you have this linked list, and in this linked list, you have 10, 20, 30, and 40. Now, keeping this thing in mind that queue operates in this fashion, let's suppose you have 10, 20, 30, and 40. Now, if next item arrives, it should arrive at this position, right? We are inserting from the rear end and we are deleting from the front end. Now, deletion from front end is possible in a constant amount of time because we know the head, right? Now, if you want to implement it, now let's suppose we want to implement the enqueue operation, right? And that too in a constant amount of time. But if we are implementing it using a linked list, now the next element, if we want to insert, is 40 and it should be here. Now we don't have anything with which we can keep track of this thing, right? The tail. Now what we have to do, we have to traverse one by one. We have to traverse to when we are at the position where the next part is null. Unless and until we find that next which is null, we need to traverse. So it will take a big O of n time. That means this operation is done in a linear time, big O of n. Okay. Now, obviously, we can modify it, and we can use or insert items in such a way that we are keeping the track of the tail, with which we have, if we have this tail in place, then we can easily perform this operation in a constant amount of time. But let's not go into that, and let's try to implement it in a linear way. And maybe on your own, you can try this. You can keep the track of the tail, and with which you can insert directly at the end, thus making this enqueue operation to work in a constant amount of time. Now, we are not going into that constant implementation. We are going to see the linear implementation. So it will be similar to what we have already seen, insertion at the end. The operation that we performed on linked list, that insertion at the end, we are going to do the same thing. So you have this element which you want to insert, right? And then you have created a temporary variable which is also pointing to p, that is the head node, right? This is your head, and temp is also pointing to this. We have already seen how we have defined this structure node, And in this, what we are going to create a node. In that we have data part and the next part. And in our data part, that is, this is also the MP1 is pointing to this new node that we just created. The data part is the element. Let's suppose 5. We want to insert a 5, and the next part is null, and it will always be null because we are inserting at the end. Now there will be again two scenarios which we have already seen. One, when your head is null, and the second, when you have some items or some nodes in the linked list. It can be one, it can be many. Now, if this is the scenario where your head is null, and that time directly you go ahead and put this head node, you can point this head node to this TMP1. Thus, you are inserting at the end, because in this case, you're performing it in a constant amount of time. Because this is a scenario wherein your linked list was empty, and this is performed in a constant amount of time. But when this is not the scenario, right, when you have 2-3 nodes, let's suppose, let me just clear it out and let me show it again how it works. So you have these nodes, and this has 100 as the address, 200 and 300. This is obviously null. This, let's suppose this is 10, this is 20, this is 30, and let's suppose this is 200 and this is 300. Okay, done. This is your P. Now we are taking into consideration the second else part. Let me just change the color as well. So we are pointing this TMP because we don't want to lose the head. So we have this temporary variable of type node also pointing to this head node. Okay, then we created a new node. Let's suppose this is our new node and we want to insert 40. This might be having some address. Obviously this will be having some address, that is 400, and this is TMP1 is pointing to this, and this part is null. So these four steps are done. Now our P is not null. It is pointing to this node, the first node. Okay. Now this part will be executed. So what we are going to do, obviously we are performing it in a linear time, so we'll be traversing to the end, right? So we are checking if TMP's next is null. What is TMP is this, is its next null? No, it is not null, it's 200. So update it, put TMP equal to TMP's next. So TMP will not be pointing to this node, now it will be pointing to this node. Again we will check, is TMP's next null? No, it is 300. Then what we are going to do, again we are going to put TMP is next into TMP. Again, now this is pointing to 30 or this node, right? So is TMP is next null? Yes, it is. So condition is true. We are out of this while loop. Now what we are going to do, we are telling him whatever is in the temp, or whatever is in this temp one. So it is 400. Please go ahead and put it in temps next. Temps next is null. So 400 is inserted here. Now what is happening? This node comes in here, and this is obviously null, so this will be 400. Done. So this is how you perform NQ operation. Obviously we are not implementing it the way we should, because this operation, NQ operation, is done in a linear amount of time. Since we haven't seen the implementation of linked list wherein we are keeping the track of the tail node or the last node, if you keep, while you are inserting elements in the linked list, if you keep the track of the tail, then easily you can perform this operation in a constant amount of time. Here it is done in a linear amount of time. Okay, so that is something that you can do on your own. Okay, done. So this is NQ. Now what about DQ? Obviously now dequeuing is simpler in linked list, right? Now if you want to dequeue, so obviously these will be the elements 10, 20, 30. If you see in this in the form of queue, so these are the elements, right? Now if you want to dequeue, you have to dequeue this because this is a friend, right? So easily you can remove this directly, and that can be also performed in a constant amount of time. Why? Because we know some operation that is there, that is deletion at beginning. So you're deleting always from the beginning, so always you have the head node that is pointing to this node, so or P in this case is pointing to this node. You can easily delete this or remove this element, right? You can perform dequeue in a constant amount of time. Now let's clear this out and let's see how it is done. So let's suppose you have again two scenarios, right? You have 100 over here, you have 200, you have 300, and then let me change the color. You have data part 10, this is 200, you have 20, this is 300, you have 30 and this is null. Now this is one scenario. The second scenario is this is obviously P is pointing to this. The second scenario is this is null and P is pointing to this. Done. Now what is happening? Since this TMP is, I think this is not required in this. Okay. So is P equal to null? In this case, yes. Then you cannot delete any elements. This is the condition for underflow. Okay. Obviously, you can use something like is empty and you're checking is empty. Is our queue empty or not? You can use that also. Okay. Since there are no elements, so no element to be deleted. Done. But what if this is the scenario? Now here what you are going to do, first you will print whatever is in the piece data. So piece data is 10. So you are printing out this is the element that has been deleted. Okay, you have printed it out. Then the next thing what you're doing, you are updating your head node. So it will be nothing but P is next. So P is next is 200. So this is your new node. Done. Also you can just remove this link, right? Or therein you have to just keep a track of this, right? If you have used this, let me just clear it out. So how to remove this link as well, because obviously you might be thinking this link is still there, so you can remove it easily. So what you're going to do, just remove this. So you have this temp still pointing to this, right? You have this temp still pointing to this node. Then what you will do, temps next equal to null. Okay, so this will be null. And now this has been removed. Okay, this link is removed. Done. So this is how you perform the queue operation, and that too in a constant amount of time. Now let's move ahead. Now is full, the function or the method that is there is full. Is this possible in a linked list? Right? In arrays we have seen, okay, if array is full, that means if the size of the array is equal to the actual size of the queue, then we say we cannot insert any element in the queue. That is, the overflow condition is always there when we implement it using arrays. But is it possible in linked list? No. Why? Because there is no such thing as static size in linked list. Linked list is a dynamic size, is of dynamic size. That means we don't specify the size. So that is why there is no overflow in the queue while we are implementing it in a linked list. Okay, so this is not possible. Is this possible? No. Okay, done. So is empty, obviously we are going to check if our queue is empty or not. So what we are going to do, if P is equal to null, that means queue is empty. Else we can say that queue is not empty, because then obviously it will be pointing to something, right? The first node in our case, this is our head, right? Done. This is empty. Now the final method that is there, we want to display whatever is in the linked list. So it is similar to what we have already seen. So we have this temporary variable. Let me just quickly draw a linked list. So we have this P and we have this temp also pointing to this. So you have 10, 20, 30 and 40. Obviously these will be having addresses that will, let me just quickly change the color and just show you. So let's suppose this is 100, this is 200, the addresses, this is 300, this is 400, and this is 100. Okay, this is 200, this is 300, and this is 400. Okay, and this is null, obviously, right? So this is your linked list. So you have TMP that is pointing to this. You will check, is TMP null? No, it is not. Print data, TMP is data, that is 10. Then put your temp pointer ahead. So temp is pointing to this now. Temp's next, right? So is temp null? No, it is 200. Print temp's data, that is 20. Move temp ahead. So temp is pointing to this. Is temp null? No, it is 300. Print temp's data, that is 30. Now next step is that put temp equal to temp's next, that is 400. Is 400 equal to null? No, it is. Is temp equal to null? No, it is 400, right? So then we print the data and then we move it ahead and put it to temps next, which is null. Then we check, is temp null? Yes, it is. We get out of the loop and we have all the elements printed. So the time complexity associated with this display method is big of n. Now let's try to implement this using code blocks, and the language we are going to implement it in is C. So now if you can see that we have these library functions over here which we have used. Then we define the structure of the node, that is data part, and the next part, which is obviously self-referencing pointer. We have also defined these variables which are of type node, so that we don't have to pass them to every function. Done. Then we have this insert, end, in delete, from beginning, display, and is empty methods that we are going to implement. Then we have this driver method, that is our main method. Then we have this value, which is the value that we want to insert, and the n, that is the choice. Okay, so from at the start of the linked list, p is null, that is our head. And then we are creating this menu wherein we are, if we press 1, we are going to enqueue. If we press 2, we are going to dequeue. 3 is empty, 4 for displaying it, and 5 to exit. Then we enter the choice and we insert a value, and we store it in n, and then we pass that n to the switch case. If we have pressed 1, and we are going to call insert at end, that is our enqueue operation, and then we are going to break out it. If we have case 2, we are going to delete. If 3 we have entered, we are going to check is empty, 4 for display, 5 for exiting. And then we also prompt a user a message, do you want to continue? If he or she presses Y, that means yes, we want to continue. Then we are going to start this menu and start this whole process again. Now we have already seen the insert function. That means we are inserting at the end, and this is obviously taking big O of n time. I also told you what is an alternative and how you can solve this problem, and so that this insertion or enqueue operation takes constant amount of time by keeping a track of what the tail node or the last node. So what we are going to do, we are creating this temp one, and we are setting its data and next part. Then if it is null, then that is our head node, that is our new node, we have inserted it. And if it is if we have some elements or some nodes available, we are going to traverse, and then we are going to insert at the end. So this is insertion at the end, which is our enqueue operation, and our dequeue is obviously performing well than the insertion at end, that is our enqueue, because we are performing it in a constant amount of time, because we have an operation where we are going to delete from beginning. Okay, we are just going to delete from beginning. Then we have this is empty condition or is empty method, wherein we are going to check if our queue is empty or not. If p is equal to null, that is our head node, if it is null, we are going to say queue is empty, else we say our queue is not empty. This is our is empty condition. Then our dequeue operation, wherein we are going to delete from beginning. That is, we are going to first check if there is any element or any node available. If yes, then p will never be equal to null, right? And also I showed you that this can be removed. This is used for removing that link that we have already seen, right? So we check if p is null, if head is null, then we say this is an underflow condition, we cannot delete anything, else we will delete and print that element. Done. This is deletion, or you can say this is our dequeue operation. Then finally we will print with the help of this display method. Right over here we will print all the elements that are present in our queue. So now let's run this thing. So here we have our menu in place, and you see if we press 1 we can enqueue, if we press 2 we can dequeue, 3 to check if our queue is empty or not, 4 to display, 5 to exit. So let's press 1 and let's enqueue. So let's enqueue 10. Do you want to continue? Yes, press Y. Again we want to insert a value, that is 20. We press enter, we press Y. 3 we want to enqueue again. Yes, we press 30, insert a value 30, we press enter. Do you want to continue? Yes. Now let's try to display all the elements that are present in the queue. So there will be 10, 20 and 30. So we press 4 and we have 10, 20, 30. This is the queue. Do you want to continue? Yes. Now let's try to dequeue. So dequeue works in such a way that 10 should be removed because that is the friend, right? So we press 2 and we should get the output as 10. So 10 is element deleted is 10. Done. We want to continue? Yes. Let's try to see if the queue is empty or not. Right now it should not, it should say that queue is not empty. So we check, we press 3. So queue is not empty, correct. Now let's continue again. Now let's press display DQ is done, display is done. Now let's try to display again and let's see what are the elements. So 20 and 30, which is correct. Do you want to continue? No. You press any other letter or any other character apart from Y. So I press N, so I don't want to continue. Press enter. That's it. Done. So in this way, we have implemented queue using linked list. And what we have seen dequeue operation, that is nothing but deletion from beginning. We have seen enqueue operation. Obviously, that is not efficient, but it will work. And obviously, I have shown you, I have told you that how you can implement it in a constant amount of time. This is constant amount of time, right? Dequeue is done in constant amount of time. Here we have done insertion at the end, right, which is obviously performing in a linear amount of time. So if you somehow keep the track of the tail, you can obviously perform it in a constant amount of time. We have also seen is empty. We have also implemented is empty to check if our queue is empty or not. And finally, we also check the display method, which is used to display all the elements in the queue. Now, one more thing is there. This is also done in constant amount of time, is empty. Now, one more thing is there, that is full method. We cannot implement it because queue is never full, or you can say that only the case when you have exhausted all the memory in your system, right? That will be the case. So in this linked list, we don't implement is full because there will be no overflow condition, and this is to check if we want to delete, and is empty is used to save us from the underflow condition, because if we have is empty condition and then we want to dequeue, that is not possible. So this will help at that time. Now let's talk about advantages and disadvantages of queue. First, we are talking about advantages. So it follows a principle of FIFO, or the elements are stored in a FIFO manner. That means, let's suppose this is a queue, and in this queue you have elements. So the deletion will take place from the front, right? And the insertion will take place from the rear side. So this is known as dequeue, the deletion, and insertion is known as enqueue operation. And both these operations are performed in a constant amount of time. So that is one of the advantages, right? And the insertion from beginning and deletion from end takes a constant amount of time. Plus, if we want to do peak first, peak last, all these operations are performed in a constant amount of time. And this is most widely used data structure when we talk about CP, that is competitive programming. When we talk about competitive programming, this data structure is most commonly used because of these features, that all the operations that are performed like insertion, deletion, peak first, peak last, enqueue, dequeue, all these operations are performed in a constant amount of time. Now let's talk about disadvantages. Since we are only able to delete or insert from the front and the rear, that means deletion from front and insertion from the rear. So the restriction of insertion or any manipulation, right? We have a restriction over these, right? What? These operations, insertion and deletion. So this restriction is always there. And so this data structure, that is the queue, is not much flexible, right? We are fixed. We can delete and insert element in a fixed pattern or in the FIFO manner. Thus, it's not much flexible.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions, and I will respond to your comments.